So now that we know how to generate our own artificial dataset, let's see how we can use this tool to simulate the real-life scenario of a data scientist. And to do this, we start by making an observation. It is impossible, as a data scientist, to collect all of the data that you would want. Let's make this more concrete with an example. Let's say that you want to measure the average height and weight of all of the pets in the United States. Now, theoretically, this means that you'd have to measure the weight and height of each individual pet in the entire United States. And then from this enormous data set, compute the average of these two quantities. Now, this is of course impossible, because once you've collected your last data points, your dataset will have changed. There will be new pets added, and unfortunately, some pets will have died. Therefore, you decide to only measure a subset of pets, let's say 150. Then you calculate the average height and weight of these 150 animals, and you take this result as a proxy for the entire population. Now, this procedure of taking a subset, computing the statistic, and then extrapolating comes with a number of drawbacks. But before we look at them, let's first introduce some terminology. The entire theoretical dataset, which you will never have access to, is called the population. And then the subset, which you will work with as a data scientist, is called the sample. And then the science and art of statistics, and arguably the reason why we need statistics in the first place, is to extrapolate our findings and conclusions from our sample, so our subset, to the entire population. Now, coming back to the drawbacks of sampling a population, there are basically two large ones. The first one is that we introduce uncertainty. Because we only take a sample, a subset of our larger population, this means that we don't take into account all of the information to compute the average. And therefore, this average will be only approximate for the average of the entire population. And thus we lose information, and thus we introduce uncertainty. Now, the second drawback is an assumption that we make each time that we sample a population, namely the following. We assume that our sample is a representative sample of our population. Now let's see what this means visually. In this scatter plot, the light blue dots represent the population data points, so all of the data points, most of which you will never have access to. And the sample will be the blue dots, the dark blue dots. Now in this case, we see that our dark blue dots are roughly distributed in the same way as our population is. However, it could also be the case that your sample is not representative. And an extreme example of this would look something like this. It's the same underlying data set, all of the light blue dots are exactly the same, but at this point, the dark blue dots are at the extreme ends of our distribution. So this sample clearly is not representative, and any average or any other statistic or insight that we derive from our sample will not be representative of the overall population, and thus some faulty conclusions will be drawn. Now, how could we get such a non-representative sample? Now, it could be just through sheer luck. Each sample is a subset of the population drawn randomly. Now, there are a lot of different subsets, and you could get unlucky by just drawing this specific unrepresentative subset or sample. But in most of the cases, unrepresentative samples are due to biasing processes. And to make this concrete, let's think back of our example. You want to get the average height and weight of all the pets in the United States, but of course you live in a very specific place, for instance in New York City on the East Coast. So you go out and you measure the height and weight of, let's say, 100 animals in your local neighborhood. But it could very well be the case that your neighborhood specifically has particularly tall and heavy animals compared to the rest of the United States. Therefore, your sample will be very heavily biased towards heavy and tall animals, and thus the average will not be representative for the average of the entire population. And this somewhat extreme example nonetheless exemplifies the scenario of all data scientists. You are given your own sample of data, but you're asked to answer questions about the entire population. So how do we simulate this scenario in our Python code? Well, let's see. And this brings us back to the same cell we had in the previous lesson, where we generated two artificial data sets. And now we can understand why I call them population 1 and population 2. Because we chose the number of data points in this dataset to be very large, 100,000 in this case, these datasets will serve as the population datasets. These are the theoretical datasets that represent all of the data, but which in real-life scenarios is inaccessible to the data scientist. Here, however, they are accessible because we have generated them ourselves. So how can we now use these generated populations to simulate the real-life scenario for a data scientist, where we only have access to a sample dataset? Well, this can be done very straightforward by literally sampling the population. In this first line, we define the number of data points that we want to have in our sample dataset. In this case, we take 40. And then we define a new Python array that will represent our sample dataset. So we call it sample1, and we put it equal to numpy.random, because we're dealing with random numbers, and then we add .choice. This choice function takes in two parameters. The first one being the Python array from which we are going to randomly pick or sample a different number of numbers. In this case, for sample 1, we want to sample our population 1. So we put as the first parameter pop1. The second parameter is the size parameter and just says how many choices or how many data points we will pick from our population Python array. And we will of course take this to be nsample, 40 in this case. And so what this line does, it basically takes our original population, the Python array pop1, and it at randomly picks out 40 data points. And these 40 data points will represent our sample dataset. And the same can be done for sample 2. And now in this cell, we have 4 Python arrays. We have two populations, population 1 and population 2, each with 100,000 data points, which in aggregate form a normal distribution. And then correspondingly, we have two samples, sample 1 and sample 2, which are randomly chosen data points from the corresponding population. Now, of course, we want to visualize this in the same way as we did before, by visualizing the histogram. And we can do this in the same way as before. We again have our figure and our axis, which will be a subplot. This code we used in the previous lesson to generate the histogram of our populations. Now, this code will be the exact same thing, but instead of our population 1 and population 2, we use sample 1 and sample 2. And all of the rest is exactly the same, except of course the title and the legend. So if we do this, we run this cell again, we go down and we see indeed two histograms now. On the left hand side, we again have the histograms of our populations, which don't change at all because they are so robust under the sheer number of data points. And on the right hand side, we now have the histograms of both sample 1 in blue and sample 2 in green. There are several things that we can learn by looking at these sample histograms. And let's start with the visual aspect. The sample histograms, they are messy. They do not exhibit this nice emergent shape of our population histogram. In fact, if we would just start with our sample histogram and look at it, it will be very difficult to derive that these samples are a subset of a population set that are themselves normally distributed. Additionally, for these sample histograms, it's difficult to derive around which value they are centered and thus what the average value is. For instance, for sample 2, the green histogram, it's very difficult to really see that it is centered around 1.5, even though the population from which it is derived is clearly centered around the value 1.5. The second thing that we can learn by looking at these sample histograms is apparent when we run this cell over and over again. We see that each time that we run this cell, we get a different sample histogram, whereas the population histogram simply remains identical. So let's understand why this is. Each time we rerun this cell, we construct a new pair of samples by choosing 40 data points out of the corresponding population, which has itself 100,000 data points. Now, because there are many ways to choose 40 numbers out of 100,000 numbers, each time we will end up with a completely different sample, and thus with a different sample histogram. And this raises a crucial point about being a data scientist. Namely, as a data scientist, in a real-life scenario, you are only given one sample, the data that is presented to you. And this again boils down to the core of statistics, namely that you are given the information of only one sample dataset, but you are asked to answer questions about the underlying populations. Now, in later chapters, we will see and learn how to handle this scenario and how to make it more quantifiable. But here already, with these histogram visualizations, you can appreciate the difficulty. As an example, let's say, for instance, that you're given two sample datasets. And the question that they ask you to answer is whether these two sample datasets are coming from the same underlying population or from two different underlying populations. Now, of course, you can visualize your two sample datasets, and that would, for instance, give you this sample histograms. Now, you can look at these histograms as long as you like. It still remains incredibly difficult to answer this question based on your sample, because looking at these sample histograms, it is not at all clear that these two different samples come from the same underlying population or two different underlying populations. Of course, because we are generating our own data set for educational purposes, on the left-hand side we see that the underlying populations clearly are different, but that's only because we can see the population histograms. But in real-life scenarios, we don't have access to them. And this just shows the difficulty of trying to answer questions about populations based on small sample sets. But of course, we will learn how to do exactly that. Now, we can make this exercise easier or more difficult by just changing the parameters. Let's, for instance, change the parameters of our populations such that they are much more distinct than they are now. If we run this cell, then we indeed see that the populations are much further apart from each other, and therefore the corresponding samples are also much easier to distinguish. However, if we then change the variance of both of our populations, then we see that it again becomes very difficult to see, even more difficult than before. It could even be the case that if we make these two populations exactly identical by putting their variance equal to 0.5 and putting both of the locations or the means of these distributions to 1, then we know that the populations, of course, are exactly identical. But it could be the case, if we just run this cell over and over again to get different samples, that we get a sample for which it is likely that we were to conclude that these distributions are in fact different from each other. For this pair of samples, for instance, we might conclude that the green sample is much more skewed to the left-hand side, even though we see from their populations that they are exactly identical. Now, one way to make this exercise also much easier, let's make the populations again different from each other, is to increase the number of sample size. And this corresponds to the strategy that I already alluded to earlier in the course, that whatever statistics that you know, the best strategy is always to increase the number of data points or to collect more data. Let's say that we increase our sample size with a factor of 10. Then we see that also from the sample histograms, it becomes much clearer that these are indeed coming from different underlying populations. And now that you know how this code works, I strongly recommend that you play around with these numbers and see how you can change them to get more insights in the underlying concepts. Now, before we go back to the slides and conclude this lesson, I want to draw your attention to one more visualization. This bottom graph basically combines the two upper panels into one visualization. Namely, the histograms that you see here are the population histograms shown in the top left panel, whereas the very fine vertical lines are the very specific values for this specific sample set, of which the histogram is in the top right panel. Now what this does is it goes back to what we initially talked about representative sample sets. For a representative sample set, most of the sample data points are drawn in this middle region for each histogram, whereas more extreme samples are more in the tails of these histograms. For instance, this point right here, which is clearly an outlier around -0.5 in sample 1 histogram, we see occur here in the very tail of our population histogram. And so we can say that this specific sample point is not representative. But because most of our sample data points come from this middle section of our population histograms, we can say that this is indeed a representative sample. And we can see this in action by just running the cell over and over again. Here again, we see that most of the sample data points represented by these vertical lines are coming from the bulk of the population histogram. If we run it again and again, we see that this is almost always the case. So let's now go back to the slides and conclude this lesson. And we conclude by reiterating the central idea of statistics, namely that you are deducing population insights from sample analysis, and that the sample that you are given is really a random subsample of the population dataset. And because of this random subsampling of our population, that we need all of the statistical tools that we will learn about. And in this lesson, we looked at it from a very visual point of view, where the sample histogram changed from sample to sample. Now in the next lesson, we will make this all more quantitatively by looking at the specific statistics of each sample, for instance, the mean or the variance. And we will also see how these change within each different sample.